Good morning, evening, afternoon, whenever you're listening to this. I apologize for not being in class today, but we'll get through this. Not an ideal subject or topic for us to do via a video, but this video is going to be amazing. Here we go. Um, when we started this chapter, we looked at this function sign. Actually, we zoomed in and we said, hey, that's y equals x. But then I zoomed out and I tricked you. And we spent some time developing a way to approximate this sine function. We started with y equals x and said at a pretty close to zero zoomed in level, these two functions look pretty close to each other. But as you can see, they separate as we get further out from zero. So we did some algebra. I don't know if you remember this, but we subtracted some things. We looked at some differences, and we came up with some other functions. Um, we came up with a x cubed over 6. And I kind of led you to these other ones, an x to the fifth over 120 or an x to the seventh over 7 factorial. Um, and because we could have guessed any number. It didn't have to be 120, it could be 119, 118. 120 is just what I decided was the best place to stop. And it turned out to be factorials. That was sort of the pattern that we had developed. But that pattern was something that I gave you. It wasn't something that you were able to come up with on your own. And this isn't a very repeatable process. The algebra involved in this was a lot of guesswork. And so we are going to, in this section, take advantage of some calculus and actually come up with these polynomials ourselves. And the goal of this, we don't know what sine of x is. If I plug in, if I want to figure out what the sine of 1 is, I have to use my calculator. And how does my calculator know? I don't know what it is. But if I can write a polynomial that approximates sine of x really well, then I can plug a number into that polynomial and get an approximation for sine of x. This is very similar to us using the first 5 terms to approximate our series, our infinite series. It's not exactly correct, but it's within some margin of error that we can deem acceptable. And so these polynomials that we're creating, polynomials again, x to the whatever power, these are just multiplication and division questions, which we could theoretically do by hand to approximate the sine of, say, 1 or the sine of 2 or whatever we wanted to do. So let's look at how we do that using some calculus. And what I'll do here is switch this to a different function that's a little bit easier to handle, e to the x. Now, e to the x is a great function. Is it dark enough for us? Let's see if I can go into, a little bit better. E to the x is a function that's nice because the derivative is the same, the integral is the same. We can do some things pretty easily with it. So what function would I, thinking about back to that sine equation, I use y equals x as my first approximation. But what should I use here? Well, I could just use the equation y equals 1. Now the equation y equals 1, let's change that color so we can see it better, blue. Let's change this to black. There we go. Y equals 1 does an okay job of approximating e to the x directly at x equals 0. They're the same value. In this case, the function values are the same. But obviously, it's not a great approximation. It's wrong on either side almost immediately. So one thing we could say is, okay, the function values are equal to each other, but what if I try to make the derivatives equal to each other as well? Because as we know, a tangent line comes through pretty nicely, and it just skims the function, but it's a better approximation than this. So if I had the line, let's just do it on the same one. I don't know. I don't want to keep adding. 1 plus x. Now we can see that not only do the function values equal each other right here at x equals 0, they're both 1, but the slopes are also the same. The slopes are also 1, I guess. And we could take a derivative. E to the x derivative is e to the x. We plug in 0, we get 1. The slopes are the same. Okay, but can I keep going? I now have the function the f value is the same. I have the first derivative is the same. Could I make the second derivative the same? Could I change this line to make the concavity match? Well, absolutely. I could say plus x squared divided by 2. Now the function value matches, the slope values match, and the concavity matches. And I could keep using these derivatives and keep adding to my polynomial to now not only make the first and second derivatives match, but also the third derivatives match. And I could make the fourth derivatives match and the fifth derivatives match, and so on and so forth. That's our goal for what we call a Taylor polynomial or a Maclaurin polynomial. These polynomials are created using derivatives instead of using our algebra that we used for our sine graph, because this algebra is not something that we want. We're not in AP algebra, kind of where. So here is, I kind of ran through the Desmos there because it's easier to visualize via the computer than it is in person. In person, I could just show you these, but you can't see my hands right now. So these 3 or 4 graphs are just doing what I just said that we were going to do. The function values match, the derivatives match, the concavity matches, the second or the third derivatives match up. And as we get those derivatives to match up more and more, our approximation becomes closer and closer to the actual function value. Just a side note here, you can read a sentence if you want to, but one thing I just want to say is that we're going to call these polynomials capital P sub n. N would be the degree, much like we said, like S sub n is the partial sum. So like S sub 7 was the first 7 terms. P sub n would be a polynomial with degree 7. P sub 7 would be 7th degree polynomial. We'll see that example here in just a second. I wanted to show this and show how we can talk about polynomials in a general way, different than what you're used to. Normally, back in Algebra 2, I'm going to erase this, but I'm going to write it right here. Normally, we'd see this like ax squared plus bx plus c, right? That's a normal polynomial with a's and b's and c's. The problem with this is that a's and b's and c's run out. We only have 26 letters, and so we can't have a polynomial bigger than a 27th degree, which we won't. But in general, theoretically, you could. So instead, we're going to call these polynomials. We're going to use different coefficients, and we're going to use some subscripts for these different coefficients. And we're actually going to write them backwards. I know that it's nice to, or we typically want to say that we want to write the polynomial with the highest degree first, in descending order. But in this case, we're going to have theoretically an infinite polynomial of infinite powers. It could be as big as we want it to be. And so we don't want to start at the end when we don't know what that end is. We want to start at the beginning and then build up from there. So our first term is going to be denoted as a sub 0, a little a sub 0. Now, different textbooks, different people use different letters. You could use C for constant. We'll use A just because that aligns with what the textbook does, but it's just any variable. Our next term will then be a sub 1x, right? That's the first degree term. And then as you can kind of see, it keeps going a sub 2x squared, a sub 3x cubed, a sub nx to the n. So these subscripts and the powers match up. Again, a lot like a sub 3 was the third term, kind of the same thing in this case. We have this a sub 0, so it throws us off a little bit. But the cubed and the subscript are always going to match up. So a sub 4 goes with the x to the 4th degree in our polynomial. Okay. So we're talking about derivatives. We're going to take the derivative of each of these things. I'm going to take the derivative of my polynomial in general, which gets a little bit ugly. I'm going to drop off some terms as we go, just because there's so many of them. But the one thing that we do know is that the derivative of a constant is 0. So that a sub 0 term here, this is just a constant. There's no x attached to it. When you take a derivative, that thing's going to disappear. What's going to happen with this? Well, the derivative of something times x is just that thing, so that should be a sub 1. Our 2 will come down and we'll subtract the power. Our 3 will come down and we'll subtract the power, right? And so we should see a pretty recognizable derivative. In general terms, unfortunately, it's not a specific function, but our a sub 1, let me just highlight that. Our a sub 1 went to just, or sorry, a sub 1x went to a sub 1. This one, the 2 popped down in front. This one, the 3 came down and we subtracted a power, right? And we keep going, which is fantastic. And if we wanted to find then the second derivative, well, the same thing happens. This thing is going to go away. This x is going to go away. So we should just get a 2a2. This 2 will pop down again, and I'm going to keep it in that format. You'll see in here in a second. So this, where am I? This 2a sub 2x just turns into a 2a sub 2 because the x went away. This 2 now came out front, and then we subtracted a power right there. And I'm going to keep it in this order because I don't know if you'll notice this because I didn't write out too many of them, but the next one would be a fourth eventually right here, and then that 4 would eventually pop out front, and then the other one would be fifth, and that fifth would pop out front, and then it'd be a 6, and that 6 would pop out front because we have here, we can keep going like x to the 4th over here. Plus x to the 5th, plus x to the 6th. And all these powers eventually will come down front in front of the coefficients. And so we get a very nice little equation. I wanted to add one more thing here, I think, of like n factorial a sub n. 3 times 2 times 1 is a factorial. 4 times 3 times 2 times 1 is a factorial. So we have an n factorial a sub n, which is great because we did, we worked with factorials. So let's actually take a look at this e to the x. I blocked out a lot of things, and we're not going to write them because that's just going to take too much time. You might have them if on your notes. If you want to just watch this and look at the notes later, the notes are kind of overwhelming. So I just wanted to go step by step. So our goal is to actually now find a polynomial approximation for e to the x at x equals 0. And we can start by saying, I have my function. My function is e to the x. I have my general polynomial, which I just copied from up above. It's a third degree because it says here find a third degree polynomial. So I start here with a general third degree polynomial. And I say to myself, I want the function value at 0. I want f of 0 to equal p sub 3 of 0. And so I say that. I say f of 0, I know that. F of 0, if I plug in 0, I get 1. If I plug in 0 here, I get, well, that goes away, and that goes away, and that goes away. I get just my first term. 0 is great because it cancels out all the x's. And I can use this. I can say, okay, if my f of 0 of my function is 1, and my polynomial at 0 is a sub 0, and I want those things to match up, then I know that my a sub 0 should equal 1. Because I just want these things to equal each other. And now let's do the same thing. I want the derivatives to equal each other. I know the derivative of e to the x. Oh, shoot, I erased my. I know the derivative of e to the x. The derivative of e to the x is just e to the x. And from up above, I know the derivative of this thing. The a sub 0 goes away. The a sub 1 drops down. The 2 pulls out front. The 3 comes out front. And when I plug in 0, this is going to go away. And this is going to go away, right? And I know what this is here because I still know that e to the 0 is 1. All these things disappear, so I get p sub 3. The first derivative of my polynomial is just a sub 1. And so what does a sub 1 equal? 1. Great. Now those first two are nice and easy because there was no coefficients. We'll start to see here some coefficients kind of come into play. If I take the next derivative, oh great, e to the x is still the same thing. It's still e to the x. Fantastic. My derivative from up above, the x here goes away. The a sub 1 goes away. I'm left with a 2a2. The 2 comes down front. I get a 6. That's my 3 factorial. And if I plug in 0 again, I get 1, and I get 2a sub 2. So I'll have to do a little bit of division here, a little bit, and divide this 2 to this side. But I get now that my second term is 1/2. because I want this to equal this. And more specifically, I want this number to equal this coefficient. So I can solve for a sub 2 by just dividing the 2 to both sides. And now I still have the 6 over here. I can do it one more time and say I want my third degree or my third derivative on this side to equal my third derivative of my polynomial. All those things are going to go away. I pulled this 24 in just because I didn't have it over here is missing. And I get this. My third derivative at 0 is still 1 because e to the x is nice that it just stays e to the x the whole time. I've canceled out all the a sub 0, the a sub 1's gone away, the a sub 2's now gone away. I have just an a sub 3. When I plug in 0, all the other stuff over here goes away forever. And I can just say, okay, if 1 is going to equal 6 a sub 3, that means that my third coefficient is 1/6. And now I have it. I have my 3 coefficients here. 1, 1, 1/2, and 1/6. So if my general polynomial, my third degree polynomial is this, then I can just replace a sub 0 equals 1 with my a sub 0, and my a sub 1 equals 1 with a sub 1, and my a sub 2 equals 1/2 with a sub 2, and my a sub 3 equals 1/6 with a sub 3. And there is my polynomial. I'm realizing now that when I did the Desmos, I didn't hit the factorial button because I forgot that I had to hit that on the, I think I said x cubed over 3. I meant to do 3 factorial. I got sidetracked. The 3 factorial is 6. So this would give me here, this is kind of the polynomial that we found or that I typed in before where the derivatives match up. If I take successive derivatives of this polynomial here, the first derivative would equal 1, which matches up. The second derivative would equal 1 or 0, which matches up. So this is the process. And this process is, we don't have to actually repeat this process. We can do a lot of shortcuts. We notice here that we found these things pretty easily. And in this polynomial side, we just kind of solved for, but we didn't, this is not really different depending on, like this function would be different each time for sine of x or cosine or ln of x or whatever, but this general polynomial doesn't actually change. It's always the same thing. This is always the second derivative of our general polynomial. So we can generalize this process because this left-hand side can change, but the right-hand side doesn't have to change. And good old Pierre McLaren, I don't know his name, Mr. McLaren here, or Mr. Taylor actually, came up with a way to generalize all of these derivatives to come up with a formula. So I'll just show you these. We'll talk about them. Our first derivative, or sorry, our first function value is this. And if I plug in 0, I got a sub 0. And if I plug in 0 to my function, I want them to equal each other. That would just give me f of 0, whatever that is. In this case, f of 0 was 1, so I was able to solve for it. But in general, my f sub 0 is just, oh, sorry, not f sub, f of 0 is just f of 0. When I plug in 0, all of these things go away, and I'm left with just a sub 0 equals f of 0. So that's my first coefficient in general terms for any function. My next coefficient uses that same thing we did up above, where I take a derivative, and my a sub 0 goes away. I'm left with just an a sub 1 because all the zeros cancel out. And on the left, or on the right-hand side, it's just my first derivative. Whatever that happens to be. Again, for e to the x, it was 1, but for any other function, it could be anything. It's just the first derivative at 0. Continuing on here, we have our next derivative over on this side. That 2 was introduced here, that 2a sub 2. And so I had to, up here in my e to the x, I had to divide by that 2 and got a 1/2. I divided by 2 on both sides. And I'll do the same thing here. I get 2a sub 2 is my second derivative. So I just divide and I get my third coefficient. So we get this thing called the Maclaurin polynomial. A Maclaurin polynomial, all it's doing is it's starting here with this polynomial. Here, let's just copy this thing. It's starting with this general polynomial. I could have done this before. I did. With this polynomial here, and it says, okay, using this process up here, I know what each of these coefficients is. A sub 0 is just f of 0. A sub 1 is f primed. A sub 2 is f double primed over 2 factorial. A sub 3 is f triple primed over 3 factorial. And the pattern here is that the coefficient is just the derivative, whatever the nth derivative, so we denote that by saying the nth derivative, over n factorial times x to the n. So x to the 7th coefficient would be the 7th derivative over 7 factorial x to the 7th. Fantastic. I wrote a little process here. We're just going to find individual derivatives at 0 and then plug them into this formula. We have to memorize this formula, unfortunately. It's not given to us. We have to remember it. But as long as we can remember this term here, we can figure out each of them successively. 21 minutes. Okay. We'll do one example for sine, so we can see kind of how we found that sine function before. And then there's one for cosine, which you could try on your own, and then e to the 4x we could try. And then we'll do some other things later. I think this is enough for one day. Let's just talk about a process. Okay, so we're going to find a 7th degree Taylor polynomial, which means I want to get to a 7th derivative, basically. A 7th degree means I want to get x to the 7th, which means I need a 7th derivative. So I'll take some derivatives of my function sine. This is the process that I think that you should go through, and this is how I think you should organize your work. I've done this lots of times, and this is people do it in lots of different ways. I think this is the clearest way to do your work and then plug it in. Some people like to plug it in at the same time. I think that adds too much complexity. So I'm going to start here and say I'm going to make this a little bigger. Hold on. That's not bigger. F of, it's too big. That's going to be terrible. F of x equals sine x. And I also want f of 0. How do I know I want f of 0? That's just sine of 0, which is just unit circle 0. I know I want f of 0 because I'm centered at 0. That's c equals 0. You can say lots of things in a problem because it says centered at 0. It could say centered about 0. It could say find the 7th degree Maclaurin polynomial about x equals 0. We're always given a centered value, and a Maclaurin polynomial is centered at 0. We always are going to plug in 0 for a Maclaurin polynomial. It's like a subset of a Taylor polynomial that's centered at 0 specifically. So we have our start here. I want to find my first function, f of 0. Great. I want to find my first derivative, which is cosine of x. And I want to find the first derivative at 0, which is cosine of 0, which is 0. So I'm going to do this. I'm just going to find derivatives, which is nice for trig functions because they are cyclical. After 3, don't do any more tally marks, just say 4. After 3 is kind of silly. So then we say, what's that, sine of x? And then we go 5th is, now we're back to on the grind, right? Negative sine of x. And then the 7th degree is back to negative cosine x. Great. I think I'm going to be a little bit lazy and just do this. Maybe too much space in between here. So I'm going to just put some zeros in there because that's what I want. I want at 0, at 0, at 0, at 0, at 0, at 0. Oh, I should have done this before too. I'll be off by 1. Great. Oh, group. I want zeros here also. Is this faster? Probably not. But it's lazy. Okay, great. The sine of 0 is, sorry, the cosine of 0 is not 0. Someone say, wait, Mr. Lewis, you did that wrong. It's 1. The sine of 0 is back to 0. Cosine is -1. Sine is 1. 0. That's 1. That's 0. That's -1. We get this, I won't say it, but it's an alternating series, bumping between 1 and -1. So here's what I'll do. I am going to take a 7th degree Taylor polynomial. Um, Pause. Unpause. Time skip. I wanted to write down the polynomial in general, but not have you watch it. So here is a 7th degree Taylor polynomial equation, or sorry, Maclaurin polynomial equation with all 7 degrees in here. And all I'm going to do is this. I'm going to take my first value, my f sub 0 value, and plug it in for f sub 0. And then I'm going to take my 1 and plug it in for f primed. I'm going to take my next one, plug it in here, take that, oops, change colors. Take this, plug it in here, take this, plug it in here, take that, plug it in there, right? See what we're doing? We're just finding, oh, what happened to my -1? We are just plugging in these coefficients into the spot that they're supposed to be at, which is great. And actually pretty straightforward. As long as we can remember this Maclaurin polynomial equation, I then just have to replace things. So I'm going to replace that. I'm going to replace this, and this, that, and that, and that, and that. So this first one is 0. I didn't think of the colors here very well, did I? Shoot. I didn't plan this out. This next one is 1. It's not supposed to be orange, it's fine. This next one is 1. The next one is 0. The next one is -1. The next one is 0. The next one is what? 1. And then we have a teal color. Good luck getting the teal color down. Teal. The next one is, where's my teal? 0. Good thing I did that one. And then my last one is -1. And so I can simplify this. All those zeros just go away. And so I get that my 7th degree Taylor polynomial, or Maclaurin polynomial for sine of x about c equals 0 is 1 minus 1 over 3 factorial x cubed. The 0 goes away, so I'm going to get plus 1 over 5 factorial x to the 5th. And then the 0 goes away, and I get 1 over 7 factorial x to the 7th. Because again, all of these zeros go away. We don't care about them. And this, ladies and gentlemen, ladies, I'm a gentleman. I'm not there though. The sub might be. Hello, sub. Ladies and gentlemen, we have now, with some calculus, figured out the exact same polynomial that we used for this. What a wonderful, circular, magical lesson. No, but really, that's before we just did it with some algebra, but now we've done it with some calculus using a Maclaurin polynomial. We found a bunch of derivatives. We plugged in a bunch of zeros, and we just took those numbers, whatever they happen to be, and plugged them into into the spots that we wanted, got rid of the things that we didn't want to do, and then we got our answer. There we go. Okay, so I would encourage you to try a 6th degree of cosine. Cosine is great because it's the same derivatives. You just start here instead of there. And actually, you could just use exactly this stuff because this would be 6 derivatives of cosine and plug it in. So if you want to actually skip that, I actually don't mind. This one's a little bit boring. But if you want some more practice with something very familiar, you could use this. This one here is a little bit more straightforward, a 4th degree, so you don't have to take so many derivatives. But try it. You would just start here by saying f of x equals e to the 4x. F primed would be 4e to the 4x with a little chain rule. The second derivative would be 16e to the 4x. The third derivative would be 64e to the 4x. The fourth derivative would be, I don't know, whatever that is, 64 times 4e to the 4x, 256, right? 256. And you say find f of 0 and f primed of 0 and f double primed of 0 and f triple primed of 0 and f to the, I did it myself that time, the fourth derivative of 0. And you take those things and plug them into your Maclaurin polynomial equation, which you should already have memorized. It's been 30 minutes. You should memorize that thing. Come on, slackers. Okay, I will be back next time, I hope, and we can talk more about, this is a beefy section. I'm just going to upload these pages, just this 1, 2, I guess 3 pages for you. But then just so you know, we'll do some Taylor polynomials, which is centered at another value from C, and have some examples. And then we have this error thing that we'll talk about a little bit. So this one will take us a few days. Don't worry, honestly. Do you need to worry about this? No. This? No. 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 Yes. Right there. That thing. That's what we need to know. Everything else was just building this one equation. So I really want you to understand how we got here and why we're getting here. We're trying to make a polynomial to approximate sine or e to the x or something that we can't do by hand, but now we have the ability to. I could plug in 1 into this thing and do 1 minus a 6 plus a 20th minus 1,540 and get an answer by hand. It's incredible. Have a great day. I miss you.